Hello, folks. Welcome to Rational Science. We have a good day today, great day today, in fact, and we're going to be doing a little bit of space time. So, like I say, if you have the time, I've got the space. We're going to also answer some questions at the end of the uh, lecture, and we're going to begin with our extinction segment, as always. First, I'm going to deal with this little issue that started a couple weeks ago, where I discussed our natural diet, and I suggested that we have these canines, right? Mammals in general who are carnivores have them. And a fellow says the following, okay, related to that. He says, "Man is a meat eater, but canines have nothing to do with it." Aha. Gorilla, a plant eater, has the longest canine of any primate. And that's true. I mentioned that the other day, okay, and here it is. You can see he's got big fangs there. But so do chimps, and they do eat meat. They do kill, in fact, other chimps. They cannibalize. So exactly why gorillas have these big teeth, I have no idea. They're not carnivores. They're primarily herbivores. They do eat termites and tiny insects, apparently. I don't think they're into meat per se. I don't know if they can eat meat. And talking about gorillas, I thought I'd mention this. Their genetic diversity is twice as high as that of humans, same as chimpanzees. And there's only, about 106,000, 107,000 gorillas in the world, most of them there in those regions of Africa. And we're 8 billion. And they have twice as much genetic diversity as us. So keep that in mind, okay? And my issue with animals such as gorillas, is that we probably don't need them on Earth, dangerous animals. Uh, should we preserve them? Should we try to, like a lot of these conservationists do, they try to, see if they can save animals here and there, endangered species, and all this kind of um, work that they do. And I suggest the following, the opposite. I'm saying we should kill all dangerous animals. We don't need alligators. We don't need sharks. We do not need lions. We do not need tigers. We don't need any of these dangerous animals out there. Bears, wolves, we don't need them. And some people say, oh, but you're going to upset the natural balance. Believe me, when the mastodons and the woolly mammoths disappeared, nothing, the world didn't stop. Okay, we all kept going. And I'm sure that if today we go into the different countries of Africa that have a lot of these wild animals and we wipe them all out, I mean, completely. We kill the lions, we kill the hyenas, we kill these dogs that are running around, the wildebeest, also the zebras. Let's kill them all. Sharks, well, not sharks, but alligators or crocodiles, whatever. Let's kill them all. And I'm sure that if we go in there and get rid of them and we plant potatoes or bananas or whatever grows in each of those countries, uh, nothing will happen. In other words, the world will not come to a stop because we killed all the lions. By the way, there's only like 20,000 lions, I found out today. Last count I had 35,000 lions. So lions are dying really fast. Okay, they're on their way out. And the other reason I suggest getting rid of these animals is that we are about to become extinct. So we don't need them in our, in our last few days of our stay here on Earth. So if you're into the extinction theory and you believe that, yeah, that man is in trouble, that we're about to become extinct, um, getting rid of all these animals doesn't do doesn't even tickle us. Okay, in fact, we're doing them a favor. You might say, Bill, you're crazy. What do you mean we're doing that? We're killing them? Yeah, I mean, it's called euthanasia. It's like we don't wait for them to suffer, being the last lonely animals. Like, you had the some animals out there, different animals in different parts of the world. When they were the last ones, the last Neanderthals, for example, it must have been very, very sad to see that. Here's the last of their species. And the question is, why wait for that day? Why wait for lions to whittle down until there's only 10 or 15 of them? Lonely animals there. I'm not sure we're doing them any harm by getting rid of them today, aside from the fact that they are dangerous animals. Why do we need them? And think about that. I know people don't like me saying all that, but think about it for a minute. Do we need these animals? Would it be better off if we got rid of them? Anyways, I did say about the canines that here you have the dog, the snake, the shark, especially. They have big fangs, okay, whereas the cow doesn't. And so, to answer this fellow, I would say that no, we do not use these. We did not develop, I think, our canines, the upper ones, for protection. I think we developed them as carnivores. How the gorillas developed theirs, I don't know. All I can tell you is that some of these other animals that you saw there, like the hippo and so on, their canines come from the bottom up. They don't have canines coming down. So if you look at them, they all have, including the rhino, it's got this horn. It's not a tooth, but this horn is always coming upwards. Those are, yes, for defense. I was looking at Triceratops also had this beak, coming upwards, and then the horns, and so when you look at all this, those features I think were for defense. That's very different than an animal such as a lion, any cat for that matter, that has the upper ones coming down, and I think those are specifically of carnivores. And in fact, that's how they determine sometimes when they find bones in the mountain um, from way back when, millions of years ago. They look at the teeth and they say, look, this animal was a herbivore and this other animal was a carnivore. And they can tell because of the teeth. Or at least that's a good rule of thumb, to figure that out. Anyways, talking about lions, here's a fellow who says, what? He says, lions have a sense of time, which I said last time. They wait for the migrations of some of these other animals. Could be wildebeest, could be zebras or whatever. And they have these migrations. When they come around, the lions know that all these herbivores are coming in their direction. It's like, it's not a watch, but it is a calendar. It's like they have a calendar in their brains, and so they have a sense of time. They also, I say that, like a lion has a sense of timing, like when he hides and he waits to ambush some kind of prey, he knows more or less, intuitively, whether he can catch that animal or not, how fast he is and how fast the animal is. And based on that, he knows when to start to run after it. He's not going to run after an animal that's, a mile away. He doesn't do that. He waits for the animal to approach him. And then at some point, there's a give and take between the animal discovering the lion and running away and the lion have to act. And so at some point he runs after the deer or whatever, and and it's a timing issue. They know more or less whether they can catch that animal, knowing their own speed. So they know how much time they have. So I think that animals do have a sense of time. He says, "Are you serious? Time is a man-made concept. Period." What next? Time dilation. Remember, physics, not concepts. Okay, well, I just have to enlighten this fellow on something else, and here it is. If I can get it on the other side. Is it this? Give me a second here. and it's this, the circadian clock, say circadian or circadian rhythm, right? And there it says clocks in the eye and the pineal gland of fish, reptiles, and birds, the eyes of marine mollusks, etc., Drosophila, the fly. All these have this circadian rhythm. And so the question is, do animals have some kind of clock? And I would say they do. Bears know that at some point in the year they have to go into the cave. It's winter's coming. Then they come out in summer after sleeping it off, which is again a circadian rhythm kind of thing. And so the issue is, yeah, animals do have a sense of time as far as I'm concerned. And instead of saying, "Wow," you got to you got to argue why you think they don't. Not just say, "Oh, that's crazy," or whatever. No, answer the question. Why do you think animals don't have? Not all animals, probably. I don't know. I can tell you that some mammals, I think, have a sense of time. And maybe a rudimentary one. It's not the seconds and minutes that we have, but they do have a sense, an intuitive sense of timing. So I don't think humans are the only animals that have discovered time. Okay, here we have something that happened in the 19th century, changing the subject a little bit. And it's the British, and they took over certain parts of India and Pakistan and Burma and some of these countries out there. Okay, they went in there, and looks like now it's the other way around. Now it looks like India and Pakistan and some of these other countries are taking over England, over Great Britain. Here you see the new wave of rulers and people who have power in the United Kingdom, and none of them have, English-sounding names. In fact, most of them are from either Pakistan, descendants from Pakistan and India. So maybe we should change the flag and put the Indian flag with two Pakistani flags, side by side with a Union Jack there, Maybe we should get rid of the lion, put the tiger as the mascot, Because, yeah, the people who are ruling Great Britain now are really, a lot of them are not traditional British, okay? And that's interesting. So I guess it's reverse conquest. United Kingdom conquered India, Pakistan, the whole region. Now these people are conquering Great Britain. Okay, here we had a case, a fellow who apparently went in there and took some information and put it on the internet, and so the Pentagon and some of the defense group, and intelligence services, they were a little concerned about that, and they arrested this fellow the other day. Apparently some kind of gamer had a little group there where he shared this information, and so they made a big fuss about that. What was interesting is that I had a similar feeling to this fellow, and he's from Russia. He's one of the ministers over there, and he had the following. He says U.S. intelligence leaks may be a fake, part of a hybrid war against Russia, right? Russian Deputy Foreign Minister Sergei Ryabkov said on Wednesday that a trove of U.S. intelligence documents posted online in recent weeks might be fake and a deliberate attempt to mislead Moscow. Okay, and yeah, intelligence agencies do a lot of that. I can testify to that. They do more than steal information. They're in the business of misinforming the other side. I think that's more what they do. That's my take on that. And so you have people like Assange and Ed Snowden. As far as I'm concerned, those are U.S. government operations. They have nothing to do with spying. They're not spying against Russia. They're not spying against China. No, they're spying against the American people. Okay, that's their job. They're put there as the leaders of the United States, dissidents, political dissidents, so that people follow them and say, well, I trust this guy because the U.S. is against them. And what the guy is feeding you is what the U.S. wants you to swallow. So that's the way it works. So you got to be careful about all that. Sleep with one eye open. I can't tell you that all of them are fakes, but certainly a lot of them are. You know, the United States spends $90 billion a year in intelligence, and most of that is to keep its own people under wraps. Right? Okay, here you have this situation. We have is a fellow who went to China. He's from France. He's the president. His name is Emmanuel Macron, right? And he went over there and he started bad mouthing the United States, more or less. Okay, he said that he doesn't want Europe to become a vassal to the United States, and that the Europe in general should reduce its dependence on the U.S. dollar. He further added that Europe should chart a different course from the U.S. with Taiwan. Man, those were strong words. And this one, at least, from the Daily Beast, he said, you know, has reminded us that several deep and important global friendships of the U.S. have been sorely tested. More worrisome, perhaps, is that they may be a sign of things to come for us in a world in which we are no longer the only global superpower, and our principal rival, a global bloc led by China, is seeking to build up its own network of influence. So a lot of people had lots to say about what Macron had to say over there in China, you know, bad mouthing the United States and all that. And in fact, one of them said the following, and this was a German minister, said this about Macron. He says, the idea of strategic autonomy of the European Union, I fear, is naive, meaning that Mr. Macron was naive, right? Security on European soil without the strategic nuclear potential of the United States, at least, is unthinkable. The US and Europe are partners in values and should also be trading partners, the finance minister added, alluding to the ongoing negotiations between the Biden administration and the EU regarding the Inflation Reduction Act, a subsidy program which favors investment in the US, drawing them away from Europe. So, you know, he gave his little kick to the U.S., saying, you know, you're subsidizing your own industry, but we agree with you. Macron is, you know, out of line, saying that Europe should distance itself a little bit from the U.S. and that Taiwan is not Europe's business, et cetera, et cetera. We, you know, again, I doubt that Mr. Macron uh, really believes that or said that, uh, you know, in an honest way. Okay, so this is my take on that, and here it is, this analysis. Um, he went to Macron went to China for what? He went to sell airplanes. That's why he went there for. He didn't go there to talk about Taiwan. He didn't go there to talk about badmouth the U.S. That was all politics. What he went there is to sell airplanes. Okay, and that's what the main discussion was. Well, after they had their talks, what was the result? Well, it says no new airplane orders were announced during the visit. China said, well, we'll see. Okay, and I think that's the main reason he went there. And just to rub it in, here's what one of his Macron's ministers said. Okay, this is how politics is really done. Okay, it says Le Maire, you know, he's the finance minister, told reporters that there was a strong coordination between Paris and Washington on their positions on China ahead of President Emmanuel Macron's recent visit to the country. Yeah, so I think that's the real thing there. You know, can you imagine if Macron would have gone to China without consulting or talking with the U.S. first, or putting them on notice first, saying, look, we're going to try to sell some airplanes, so I hope you don't mind, but we're going to badmouth you. We're going to say everything that we can against you that we're allowed to. You know, like we should distance ourselves a little bit from you, and Taiwan's not our problem. And the U.S. said, okay, we understand. You want to sell some airplanes and you got to lie a little. Okay, no biggie. And that's why the Biden administration, I think, said very little about Macron. And the people who really jumped up were the Republicans who said, "Oh, look what Macron's saying," you know. No, no, he went there to sell some airplanes. That's what he went there for. He didn't do very well with that, so he had come back to France with his tail between his legs. Chinese said, "Well, we'll see if we buy more airplanes." Okay, but yeah, I imagine if Macron would have gone in there and said, "You know, we hate all you Chinese, and we think Taiwan should be a separate country, and all this and that." Said, "And by the way, do you want to buy our airplanes?" I don't think it works that way. No, no. He had to badmouth the United States, put a little distance between it and France, so that maybe the Chinese would warm up to his airplanes. That's how politics really done. That's why I gotten away from politics. Okay, how is the world doing? Well, here's the IMF's 5-year growth forecast is the weakest since 1990 for the world, for the entire planet. Okay, and it says the IMF forecasts that global economy will grow at a seasonal around 3% annually over the next 5 years. Not a very strong number. Okay, and again, I'm saying that the entire planet is getting into this asymptotic growth trend. Okay, its weakest medium-term projection since 1990. And then there's the managing director of the IMF cited geopolitical factors, stubbornly high inflation, and recent banking industry pressures for the lukewarm outlook. And it wasn't only the IMF, we had the World Bank also, and this is what they predict. And you can see that most of the countries are in the dark. The ones that are in the bright are countries that are in the developing stage. So of course, they're going to suffer some increases, some big increases in their economies in the next maybe months or maybe a couple years. But they're going to level off as well. And just now, as you can see, for the global growth, it's just 1.7 this year. Numbers are not that great for the coming years. But the ones that are going to be driving the global growth are, as you can see, all these underdeveloped nations, primarily in Africa and Southeast Asia. But what happens when they achieve, their maximum development, their maximum economic evolution? Well, after that, all I can tell you is that, we cannot have the Klingons come and buy from us. Okay, so at that point, the Earth, our humans, the human economy doesn't grow anymore. So at some point, we're going to reach that point where it's zero growth for the entire planet as far as, economic growth. So I'm saying we're getting there, and when we do, that's it for man. Okay, we don't go further beyond that. Okay, so here is another parameter, and that is the debt. Okay, especially for China and the United States, and you can see how that's going up and up. Okay, they say due to fuel increase. I think it's a question of that they have to create money, and when they create money, why? Part of the reason is so that they can pay what they owe, and it's easy to create money. All you do is just put another zero in the computer. Now you have 10 times as much, right? And if you put it at the end, not in front. But what happens when you have that situation? Well, all you're doing is creating money, but you haven't created the real value that underlies that nominal value. And you can't just keep doing that. But they have to do that in order to pay the debt. So they pay the debt in nominal value plus some interest, right? But they have to stay ahead of the game all the time. And you can't do that constantly, because then what you do is you leave behind the worker, the proletarian, who depends on his salary. And so, there's that give and take. And I'm not sure that they can overcome the debt. Debt is here to stay. And not only here to stay, but here to grow. Okay, so debt is a problem. And so we have what growth is a problem, debt is a problem, Salaries are a problem, and of course, labor, the fact, unemployment, that's also a problem. Okay, and here we have India, and looking at its population, there was an article said the country's population has more than quadrupled since independence from colonial rule 75 years ago. But in the past 60 years, the percentage of people aged 60 and over in Kerala, a town over there, a region in India, has shot up from 5.1 to 16.5. Everybody's becoming old. Some of it has to do with migration, emigration, people, young people leaving, but some of it also has to do with the fact that kids are not having kids. Okay, they're just leaving and not creating new people. The aging population combined with the migration of younger generations means there will be 35 people over 60 in the state for every 100 working age people by 2030. So the numbers are not looking very great. Okay, the state's unique demographic is in India are due to the declining what fertility and increasing life expectancies. So the population pyramid is overturning in India, and here we have Africa, which is half the population of India. Okay, all of Africa, the whole continent, about half the population of India. And look at the fertility rates. You can see that they used to have more children before, and now it's coming down for all these countries. And they think it's related to contraception, the fact that a lot of women are using contraception. Um, I disagree. I don't think it's got to do with contraception specifically. It does help, yeah, of course. That's not the main reason. What is the main reason? Well, here was an article. It says the world's peak population may be smaller than expected. And it's talking about Africa's slowing baby boom. Remember, Africa is the one everybody's counting on to take the numbers up, right, in population. It says here demographers would be more inclined to agree that these fertility declines are real and likely to continue if they could easily identify their causes. They don't know the causes. Okay? Teasing out the causality is tricky. Okay, so what's the problem? Well, they think it's contraception or family planning or girls' education, climate change. Okay, some propose that climate change is causing this whole problem. Economists in general think that poor families have more children. That's the worldly wisdom out there. And last but not least, the one that I propose is that last one there. And they just put it in there like, we saw it, but we don't pay too much attention to this. As there are often big regional differences. Fertility rates are much lower for urban women, who typically have 30 to 40% fewer children than those in the countryside. Yes, urbanization, that's what's killing population. Okay, people are moving from the country to the cities. There's this transition going on. That's the underlying cause. Okay, the underlying cause is that. Why? What happens when you come to the city? You have different economics, different culture. Okay, you have density dependent birth rates. All these things that are caused by urbanization, the fact that we are many in a small area, in a small region. And people say, well, people can travel there, nobody's holding on to them. Turns out that everybody's tethered to the city for different reasons. That's where their livelihood is and whatever. And they can't work it out there in the middle of the desert, so everybody goes to the cities. And the cities are growing, and towns are becoming cities, villages are becoming towns, and so on. Populations are growing in the cities. That's where everybody's going. When you go to the cities, you abandon the country, and a lot of the agricultural corporations buy the land. They mass produce food that later on gets sold to the cities. That's the way it's working today. Okay, and so here you have what's happened in the last few years. Urbanization rate in Africa from 2000 to 2025. You can see how it's going up, 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 and up. And you can see some of the cities there that have ballooned also. And that's actually what's happening. People are moving from the country to the cities. So a lot of these countries, by the way, they're empty. People say, oh, they're so populated. No, Nigeria is an empty country. It's got a lot of land, believe me. But that's not where people are. People are always in the big cities, in Lagos, in, all the big cities are where all these people are at. So people don't go out into the middle of the desert and say, I'm going to live here. No, it doesn't work anywhere. People go in the country, go from the towns to the cities. Okay, so yeah, this is what's happening. Um, Here I have another uh, side to that, which is density dependence. Okay, and here you see it. These are a list of animals for which it's been verified that they have density dependent birth rates. It's been measured. Okay, people have gone in there, studied them, and they made a list of at least some verified animals that when they reach a certain density, for a given plot of land or whatever, they stop having kids, or their um, reproductive rate goes down as a whole for the whole herd or whatever they are, right? So, yeah, density dependent. And by the way, humans are on the list. We are density dependent animals. Okay, we cannot avoid density dependence. It's been verified for humans as well, and that's why we're growing asymptotically as far as population is concerned. Not because there's not enough land in the world. I mean, just take Russia. It's got so much land out there. It's an empty country. And nobody lives over there on the other side of the Urals. Everybody lives what? In Moscow, Leningrad, Stalingrad, and so on, St. Petersburg. That's where people go. They live in the cities. Those are the cities that are growing. Not out there in the middle of nowhere. Nobody goes out there. But you could change the trend by creating towns somehow. Okay, and yeah, that's one of the things that they should be working on. I'm not even sure that's going to help in this day and age. But yeah, if they could create towns, new towns in the middle of nowhere, the government, create some kind of incentive for young people to go there, then you probably have an explosion of population again. I think that's the only way to do it. But it would have to be, at the point of a gun. You'd have to get people to get down there, I don't know, find gold and go as a miner or something like that, like in the 1849 to 49ers, right? Or Alaska gold. Okay, so this is what density dependent birth rates conduces to. It's the overturning of the population pyramid and eventually to what? To extinction. Okay? There is no S curve. The S curve ends in a straight down exponential decline of humanity. Okay? So yeah, there is no smooth curve for the world population. It's going to get to a point and it's going to continue growing maybe slightly, less and less and less, approaching zero. But before that happens, the global economy, I think, will collapse, and then it's going to be straight down. That's why it's not going to be a smooth curve that goes up and down forever. No, it's just going to go all the way down exponentially. Okay, let's move on to space time, our good old subject matter for today. What is space time? Well, let's begin at the beginning. We covered the following. We had space, okay? And we looked at existence, and we looked at time in the last couple of weeks, okay? Space and existence are easy. They're static concepts. They fit in a single frame, as you can see there, the yellow bracket there. They fit in a single frame of the universal movie. What's a universal movie? Well, it's a tool. That's what it is. It's a tool where we have location, only location, a static concept in every single frame of that film. So it's like using God's camera, right? And he takes a snapshot of the entire universe. He's outside the universe, right? And like St. Augustine said. So he takes a snapshot of the universe, right? And he gives you the snapshot, okay? And so you can see every atom in the universe, every star, every planet, every galaxy. It's there, but static, in a static mode, okay? Because it's just location, distance between all the objects. That's all you have in a single frame, okay? So there you can at least isolate all the static concepts. And there's a couple of them there that we use in physics: object, distance, location, existence. And we have also space, right? It's a static concept. Space is not a thing. Space is that black stuff there. What is that black stuff? Well, it's not a stuff. What it is a synonym of nothing. What is nothing? What's the opposite of something? Something is that which has shape. Nothing is that which doesn't have shape. See how easy it was? There are antonyms. You can use those terms consistently now. On the other hand, you have time. Time is a dynamic concept, and we illustrate that by showing that you need at least 2 frames of the movie, that the beige bracket on the bottom. So all those concepts there, those are all dynamic concepts. I call them dynamic because they require at least 2 frames of the universal movie. So we have what? We have space, which is a static concept, and we have time, which is a dynamic concept. How do you merge them? How do you put them together? That's the question. It's like putting together standing still and moving. How do you do that? Right? And that's more or less the situation. That's going to be the trick. How do you achieve that? And apparently, we have people here. We have one fellow who put a comment, okay, and he said the following. He says, "Existence isn't static. We are constantly moving through space, even if we're still sitting still. Our brains are of apes." Oh, okay, that explains that. Okay, maybe that's his family there. Okay, there's no reason for us to understand the truly fundamental nature of time, only what is useful to survive. Yeah, I guess if you live in the jungle, I guess it doesn't matter where, how you define time, right? It's not important, just survive, right? Talk to any real scientist and they'll admit that the limitations of these concepts, okay, that means they don't know how to define them. That's all it is. I've watched many of Brian Greene's vids. He's a down-to-earth guy and knows that we don't know squat about the universe. Yeah, Brian Greene, I guess he's proud of not knowing anything, and I don't know why this fellow idolizes Brian Greene, because, I mean, why does he follow him? Does he follow him because he knows or because he doesn't know? If he doesn't know, why make him to be such a hero? I mean, he's staying it there. In the 19th century, they had this Know Nothing party in the United States. It lasted for a while, and then it went out, and it looks like these folks have restarted this party. Now they're the Know Nothing party. They know nothing, they're proud of it. Okay? But again, why would anyone idolize a fellow like Brian Greene if he tells you that he doesn't know anything? Okay? You would think it's the other way around, that if you're looking for a physicist or a scientist or whatever, you would look for someone who can explain something and tell you something. But if the guy says, "Oh, by the way, we know nothing," oh, great, you're my hero. Okay, and here's another fellow. He says the following: "Time is a tool to record the temporal aspect of change." I like it because they come here, and they boast like, "Oh, you know nothing, but let me tell you what time is." And he says, temporal aspect of change. You look up temporal, it says of or relating to time. So that's that for that. Yeah, these people never learn how to define terms. They don't think defining terms is important. And so when you criticize them on the basis of their definitions, they say, "Oh, you're doing semantics, Bill. You're doing word salad." They dismiss that because they don't like that their definitions are torn apart so easily, and they are. So yeah, it's very important to define terms in physics. Without that, without what I call the foundations of physics, without a set of definitions of the most important words you're going to use to give a physical interpretation, you have absolutely nothing. You need to know words such as object, distance, location, exist, motion, concept, space. You need to know how to define those terms. Then you can carry out a rational discussion with someone. But if you don't know what an object is, especially, you don't know what existence means. What do you mean by exist? Does God exist? Does God not exist? I mean, then you can go on chasing your tail forever in circles. So yeah, you need to define words. Anyways, here we had in, 1911, I think it was. No, 1908. And this is Minkowski, and he said, "Gentlemen, the concepts of time and space which I would like to develop before you today, have grown on experimental physical grounds. In other words, they did experiments and they got these conclusions and they say, oh, we discovered space time. Okay? And henceforth, space by itself and time by itself shall completely reduce to a mere shadow. That's the death of time and space separately. And only some sort of union of the two shall preserve independence. So again, how do you merge space and time when space is static concept and time is dynamic? And of course, when you go out there, you don't find a definition for the word time, especially. Okay, nobody has a definition to this day that you can sink your teeth in. They all eventually say, well, by the way, we don't know how to define time. We don't know what it is exactly, but we use it anyways. We use it in our equations, and we have this space-time where we merge time with space. You know, they can do all those things, but they can't define the word time. And of course, they can't define space. They don't know what space is to this day. They say it's made out of particles that pop in from space, from the vacuum, from the void, right? And so space is made out of particles, a thing. Then they say it's infinite, like the numbers. And others say, no, it's not infinite, it's finite. And so we don't know if it's finite or infinite, if it's a thing or not. We have no idea. I mean, you know, the mathematicians, they have no idea what space is. And so they're going to take this unknown called space, they're going to merge it with an undefined term called time. And they created space-time, and they say they proved it through experiments. Okay. Here we have good old Einstein. I showed this the other day. He took that space-time, he started warping it, saying that that's gravity for you. Okay, mass bends space-time, okay? And that's what compels mass to roll around another mass or around space-time. Okay, so this is what they did. They took this concept, space and time, merged it, and now they're starting to warp it. Okay? Think about that for a minute. You know, it's like taking love and intelligence, merging them and saying, we're going to warp it now. Yeah. Okay, let's see how you do that. Okay, so what is actually space-time? Well, if you remember, for those of you who went to high school, right, you have a what is called Cartesian coordinates. You have the x on the bottom and the y on the side, right? And so what you do, you use that to locate objects, like, you know, you want to locate the position of something. You take, for example, an ordered pair, you take a number on x, could be a number 6. So you take 6 steps along the x, then go 5 steps upward on the y, and you end up at some point 6, 5, and that's a location there on that coordinate system. Okay, very simple stuff that they teach you in high school. Okay, what's happened here is they've taken that, and that's what they turned into space-time. Okay, and here's a graphic representation of that I want to show you. Okay, here it is. You have the Cartesian coordinates. Okay, and you have x on the bottom and y on the side. What they did, they turned this into this space-time thingy, and then they started, you know, warping it as well. You know, that's what they did. Okay, so what you have here is a coordinate system. That's all it is. It's a mathematical system which they turned into a physical system. Okay, they simply went in there, you know, turned it into this space-time canvas, fishnet, whatever you want to call it, trampoline, and then they put some weights in it. You know, that's mass pushing it down, figuratively. Okay, pushing it down, and that's what the cause of gravity is. Okay, so what you have is really a Cartesian coordinate system that has been turned into this physical thing called space-time. Okay, it's a mathematical concept, especially the time part. The space, I don't know about that, because again, space belongs to physics. Space is not something related to numbers. Space is that black stuff out there, whatever that is. And so you have to point to it. If it's an object, you got to show what it looks like if it's an object, if you present it as an object. So you got to show us the edges of space and label whatever's, you know, outside of it. so that we can get an idea, what is encapsulating space. That's if space is an object, a thing. And on the other hand, if you say space is a concept, no problem. That's what we say here as well. You have to define it. You have to define the word space. And we define it as that which has no shape. Okay? So it's not infinite, it's not finite, because infinite and finite are adjectives. You can only apply these adjectives to objects, to things. Space is not a thing. Space is the opposite of a thing. Space is nothing, that which has no shape. Therefore, it can't be neither infinite or finite. Okay? So that's our definition, but whoever gives the presentation, whoever thinks space is an object, has to first point to space and label space and whatever's encapsulating it. That's the way it works in science. Okay, we had the other day Mr. Augustine here, St. Augustine, and he created the notion of the block universe, which is again a synonym really of space-time. Okay, what did God do before he created universe? That's the question he was trying to answer, okay, because some people obviously asked him that question. And so he had this reasoning process. He said, God is not material, God is spirit. That comes from the Bible, right? God doesn't move, okay? God is, right, because if God is a spirit, God is a concept and therefore doesn't move. So far we're totally with him, okay? I agree here with Augustine, okay? Augustine, I call him, because he dealt so much with time. He says God is eternal. He's been there always. Why? Because he's in the present tense. He doesn't move. He's just in present tense, and that is as eternal as it gets. God is outside the universe. Okay, so the universe is something that's outside of God. God is going to create this universe. He created it and says, time began when God made the universe. In other words, time is inside the universe, which is exactly what space-time is, what general relativity says. They say that space and time are within that ball that you see there, that flattened out ball there. Okay, God is outside. God doesn't move. God is really spirit, not a bearded guy like I put there. Okay, God is a spirit, so he doesn't move. He can't move because he's a concept. Okay, so far so good. How something that is a concept created a something that is an object, I don't know. Okay, that's something you got to explain the process there. But other than that, we have God outside the universe. God doesn't move. God is spirit, right? He creates this universe, right? And it turns out this universe has space and time within its borders. Okay, we call that the block universe, also known as space-time. Okay, so let's make sure we understand that. Okay, so general relativity did not come up with that concept, the concept of block universe. It was already there from Augustine in his Confessions. His book Confessions about what was it? About 350, 380 BC or something like that, AD. That's when he wrote it. I think it was closer to the year 400. Okay. Anyways, he wrote that book, Confessions. You can look it up. And here we see good old Brian Greene, and he's going to take the block universe, which he likens to a loaf of bread. He's going to slice pieces off of it. Each one of those slices is what? Time. Again, and I discussed the other day that you can't do that because time requires at least 2 frames of the universal movie, so you cannot slice it. You cannot have a single slice. A single slice, as Brian Greene is showing there, is really location. It is not time. Okay, not motion or time. It's only location, distance, objects, space, and all static concepts such as existence. Okay. Okay. So here we have Mr. Stephen Hawking. What does he have to say? He's a guru, or was a guru until recently, of space-time. And this is what he has to say in his book, his famous book, A Brief History of Time. Einstein made the revolutionary suggestion that gravity is a consequence of the fact that space-time is curved. Space-time is curved? What do you mean? Or warped, right? And he says, how can that possibly be if space-time is a concept? What do you mean it's curved or warped? Curved and warped are words that relate to physical objects. And good old Stephen Hawking, he's treating space-time as a physical object, and he's not the only one. As you can see up there, NASA, okay, they have a picture of this. They show this space-time canvas, this fishnet, being warped by the Earth, okay, by the mass of the Earth, as so they say, okay. And the question is, here everybody's treating that as a real physical entity because they are talking about curved and warped concept called space-time. And so he continues, he clarifies just in case you didn't understand, okay? Bodies like the Earth are not made to move on curved orbits by a force called gravity. The mass of the sun curves space-time in such a way that although the Earth follows a straight path in four-dimensional space-time, it appears to us to move along a circular orbit in three-dimensional space. So the Earth actually travels in a straight path. But that's out there in the four-dimensional world, you know, tesseracts and whatever. Here on Earth, we poor little creatures, we see it in us going around in a circle because we can only see up to 3 dimensions and no more. Okay, it says the mass of the sun curves space-time in such a way that although the Earth follows a straight path in 4D space-time, it appears to move along a circular path in three-dimensional space. Okay, in general relativity, bodies always follow straight lines in four-dimensional space, but they nevertheless appear to us to move along curved paths in our three-dimensional space. He says that in his book. Here you have a guy who studied at least 10 years at the universe, and he says this nonsense. Okay, not only does he treat space and time, both which are concepts, he treats them as a physical object. He warps them, he curves them. He's going to put the Earth there, and he's going to say, well, the reason it goes around the sun, it actually goes in a straight line in four-dimensional space, but here in our world, we see it as a circular movement. Totally crazy. I mean, I don't know about the four-dimensional. I mean, I haven't drank the 10 beers that Hawking drank. You know, maybe that's what made him see these visions. All we see here is that, you know, the Earth goes around the sun in a circle, more or less, right? And the question is why? And they say, well, the reason it goes around in circles is space-time is curved. In other words, time is curved, and there's this wall. That's what they're showing. That's what they illustrate. That's what they explain. There's this wall of time that prevents the Earth from flying out of the solar system. Curved time. So you figure that out. Okay, and just in case, you might say, well, Bill, maybe you misunderstood. Here's NASA, okay? NASA, this is from their page, okay? NASA's Gravity Probe B, a little rocket they sent out there with some gyroscopes to test whether the gyroscopes would drag space-time around itself. Again, treating it space-time as a physical object, okay? It says Gravity Probe B mission has confirmed 2 key predictions derived from Albert Einstein's general relativity, right? Which the spacecraft was designed to test. Okay, the experiment launched in 2004 used 4 ultra-precise gyroscopes to measure the hypothesized geodetic effect. The warping of space and time around a gravitational body and frame dragging. You know, they're going to drag space-time around, right? The amount a spinning object pulls space and time with it as it rotates. It's pulling on on time. How do you pull on time and drag it around yourself? Jesus Christ, what are these people talking about? And we spend money, you know, taxes and so on, paying for this whole thing, okay? Gravity Probe B determined, it's already been proven, right? Both effects with unprecedented precision by pointing at a single star, etc., etc. Okay, so what are they saying? They used Gravity Probe B to drag space-time around itself. It's dragging, it's pulling on time. That's what they're telling you. These are people who have at least 10-year degrees, PhDs, and they're telling you this nonsense, this poppycock, that a gyroscope is pulling space or time, both space and time, but specifically time, because I think that's straightforward. I mean, how do you pull on time? How do you pull on a second? Okay, that's what they're saying. Okay, and someone explains also over there at NASA, says time and space, according to Einstein theories of relativity, are woven together. They're woven. Someone, I guess God wove them together. Yeah, used maybe the rope hypothesis, the rope to do this, forming a 4D fabric called space-time. They're talking about a fabric. What's a fabric? They're talking about, some kind of shirt, maybe a dress. They're talking about something. Okay? The mass of Earth dimples this fabric, much like a heavy person sitting in the middle of a trampoline. Okay, so I think you're getting the hang of this. It's not that I'm coming up with all this. These people are telling you in your face that there's something called space and time. You drag them around, you can sit on it, and when you sit on it, you push it downwards. Gravity, says Einstein, is simply the motion of objects following the curvaceous lines of the dimple. If Earth were stationary, that would be the end of the story. But Earth is not stationary. Our planet spins, and the spin should twist the dimple, slightly pulling it around into a four-dimensional swirl. So now the Earth twirls around, it's going to pull on space and or time, right? This is what GPB went to space in 2004 to check. Put a spinning gyroscope into orbit around the Earth with a spin axis pointed towards some distant star as fixed reference point, okay? Free from external forces, the gyroscope's axis should continue pointing at the star forever. But if space is twisted, okay, space, nothing is twisted, okay? The direction of the gyroscope's axis would drift over time. By noting this change in direction relative to the star, the twists of space-time could be measured. My dear God. When it comes to it, I'd rather go back to the old-time religion than the new-time religion. This stuff is beyond me. Okay, they're warping time. They're pulling on time. They're sitting on time, weighing it down, curving it, and that causes little balls like the Earth to go around in circles forever. That's their explanation. That's their physical interpretation. And of course, when you point that out to them, say, "Well, we don't understand it either." And by the way, you're bringing up a subject that belongs in philosophy. We just do equations. We don't do physical interpretations. So why did they even try? Why did they even attempt a physical interpretation if it's not part of their job description? Well, very simple. Because if they didn't, all their math would be worthless, which it is. Okay? Because all their math is leading them to conclude something about the universe that ain't so. And that is how it works. And it doesn't work the way relativity says, with space-time and time being warped. It doesn't work that way, believe me. Okay? So this nonsense that they have that you can warp time, that you can warp space, which is nothing. How do you do that? Grab a piece of space and show me how you warp it. It's very simple. Okay, but he doesn't stop there. Hawking continues because he says, look, if space-time is warped, right, guess what happens to light when it tries to travel? Well, here you have a zigzag of light. Again, the fact that space is curved means that light no longer appears to travel in straight lines in space. General relativity, what predicts, we're going to talk about that today with our science critic, right? Predicts that light should be bent by gravitational fields. So there you see how it's warped. Okay. Now he says it should be bent. I don't know how you can bend light when they say it's made out of photons. You can at best talk about deflect and deflection. You deflect a series of photons, not bend. What are you bending? Are you bending a photon? I mean, what are they talking? They don't even have their language correct. Okay? But yeah, is that how light travels in like a curve around the sun and then around the earth and so on? Well, I don't think so. Light always travels straight. Okay? Rectilinearly, it's called. Okay, and what are some of the other conclusions that Mr. Hawking comes up with? He says, before 1915, space and time were thought of as fixed arena in which events took place, which was not affected by what happened in it. Bodies moved, forces attracted and repelled, but time and space simply continued unaffected. It was natural to think that space and time went on forever. Space and time are now what? Dynamic quantities. When a body moves or a force acts, it affects the curvature of space and time, meaning that they move, and in turn the structure of space-time affects the way in which bodies move and forces act. This fellow is saying that space and time move, okay? So it's not only bodies that move, but space and time move. And I like to ask his bartender to give me the same stuff he had. Jesus Christ. Okay, and then he says, the following says, the old idea of an essentially unchanging universe that could have existed and could continue to exist forever was replaced by the notion of a dynamic expanding universe, meaning, what's expanding? Space, right? And I guess time as well, because time is expanding, right? That seemed to have begun a finite time ago, and that might end at finite time in the future. The revolution was to be the starting point for my work in theoretical physics. Okay, great. What did you find out? Roger Penrose and I showed that Einstein's general theory of relativity implied that the universe must have a beginning. Okay, so there's the beginning, a little explosion there called the Big Bang, and from there we have this bottle, or I guess a glass. Sometimes I put some beer in it, okay? Guess it fell on its side. But that is your space-time there. The time is going rightwards, and I guess space is inside each one of those frames, inside each one of those cross sections or slices, as Brian Greene illustrated. He sliced them apart. Okay, so what should we conclude from all this? Well, this is what space-time is. It started out as a coordinate system. Okay, what they did was replace width with space, and space, the three dimensions of space are there in a single axis, and they arbitrarily replaced the axis of height with time. Okay, so we have space on the x-axis, time on the y-axis. From there, they kind of turned that into space-time, and then they started warping it. So what are they warping? They're warping this concept, this coordinate system created or originated by Rene Descartes, okay, 17th century. Okay, so this is what it's all about. What you're warping is this concept. And that's what these people deal with every day. They talk about space, time, and then of course they're going to put in there black holes and wormholes and dark matter and dark energy, and they're going to fit it in that space-time. It's part of that space-time. Part of it is these other things that they've created over time, right? So we have space and time coordinate system that's been warped, and they're going to be putting these other entities, which are mathematical concepts again, they're going to fit them in there to explain especially gravitational phenomena. That's the point of it all. Okay, so why doesn't the Earth fly out of the solar system according to general relativity? Because of space-time. You have warped time. There's this wall of a warped canvas, so to speak, a warped fishnet, and it's that warpage that creates a wall, so to speak, that prevents the Earth from flying out of the solar system. The funny part is that, the Earth is not allowed to go outwards, but, we're at the edge of the Earth there, and I don't feel squashed by this wall of time. So I don't know why the warp wall of time does not squash us. Okay, that's something that they would have to explain, because it can stop the Earth, right? Because the Earth is banging up against the wall, right? It's sliding or rolling along this wall. But we're at the edge of the Earth, and we don't get squashed. So I don't know. You figure that out. How it is that the Earth can roll around time, warp time. Warp time is strong enough to prevent the Earth from flying out, but it's not strong enough to squash you against the the ground of the Earth. Food for thought. Okay, let's move on to our science critic, and he had to say something about predictions. And I guess he doesn't understand the difference between a description and an explanation. And so he tried to con his way, saying, look, if we know what happened in the past, we can predict the future. Totally irrelevant. A prediction only deals with the future, and if you just make a statement of what's going to happen in the future, all you did was utter a description. That's all you did so far. If you can explain why it's going to happen, now you're talking about the past. You're talking about your experience. He still doesn't understand that. Let's see if some of you at least can understand what the difference is, okay? Let me put them on here. Here it goes. Listen carefully. The questions and issues to be addressed in this rebuttal include: a prediction has solely to do with the future. A prediction without more is just a description. If you can explain why the prediction is going to materialize, you are no longer predicting. You are now talking about the past.
If you want to work out what's going to happen, a good idea to do that is to work out what has happened. By paying attention to what has happened, I can then work out what's going to happen. Like if I keep on dropping an object and it keeps on falling towards the ground, then I can assume that if I keep on dropping the object, it's going to keep on dropping towards the ground.
So I guess he doesn't understand. He cannot talk about explanations of the future. Explanation belongs exclusively to the past and has to do with our experience. So here's my assessment, okay? What has happened is the past, okay, straightforward. Experience is also the past. Prediction, on the other hand, is only related to the future. Prediction is only about the future. Prediction based on experience is irrelevant, okay? We don't care if you guessed it, if you had experience with it, you had a bad dream, we don't care. It doesn't matter. When you make a prediction, all you say, this is what's going to happen. So far, all you made is a statement. So far, all you did is describe what's going to happen. Prediction, something is going to happen. Okay, straightforward. Okay, that's just a description. Prediction is 100% description. That's all you said so far. Something is going to happen. It's just a description. You haven't said why. And you better not say why, because as soon as you say why, it means you're drawing on your experience. The why part has nothing to do with prediction. The why part has only to do with the past, with explanation. Okay? And because these people get so confused between explanations and descriptions, you have the mathematicians predicting the past all the time. In fact, here are 3 papers that I just pulled out of the hat out there. Okay? One says, predicting the initial conditions of the universe using deep learning. Predicting the initial conditions of the universe? How do you predict the past? I mean, Jesus. Angular momentum evolution can be predicted from cosmological initial conditions. And another says, the uncaused beginning of the universe, the prediction of a space-time singularity in our past. So all these people end up predicting the past. Why? Because again, they confuse descriptions with explanations. A prediction is only a description. So as long as you keep it there, you're okay. Now you can describe things that you see in front of you or describe things in the past as well. Describe is not a problem. The problem is prediction is only a description, but not all descriptions are predictions. Okay, so let's make sure we got that right. Prediction is only about the future. Prediction is only a description up to that point. It's a statement. That's all it is. That something's going to happen. If you can say why it's going to happen, how you got that conclusion, was it a lucky guess? Did you have a bad dream? We don't care. The point is, if you can explain why, now you're drawing on your experience, and that's only the past. Okay, so what happens, these people are predicting the past. They end up predicting, how the universe started or the initial conditions of the universe or whatever. That's not a prediction, okay? What you're doing is explaining and turning that into a prediction. Okay, they're kind of reverse engineering it. They're saying, well, if we take all these stars and pull them all the way together, yesterday closer and closer together, we end up with the initial conditions of the universe, and this is what should have happened if my calculations are correct. That's not a prediction. Okay, You're trying to explain the origin of the universe, which is nonsense anyways. But aside from that, you're explaining a theory of how the universe came to be. You're not predicting anything. But they use the word prediction a lot because it's so, it's important in mathematics to say, oh, I can predict. Oh, then you got a good crystal ball. Here's your Nobel or your Templeton Prize or whatever. So that's the way it works. Okay, let's look at some of the questions that people raised since last time. Fellow says, how is electricity actually generated in a living being? Is it the heart that generates electricity? But what then drives the heart if not electricity? Well, first, this is our version of electricity. Okay, uh, atoms are, or you could say even molecules, are bound together, physically bound together. Uh, if you look at the balloons that are the electrons, all these balloons merge. Okay, they're not little electron beads that orbit. What we're saying is they are balloons that encapsulate the atom. It's the surface of the atom. It's a membrane. It's a balloon. And when these balloons merge, okay, they form these long strings. When they, I call them serpentines, and when they spin at great velocity, that's what we call electricity. What they swing around are the threads that connect them and that form part of their electron shells, and that's what we call magnetism, okay, a field, as they call it in mathematics. Okay, so this is our version of electricity. So the fellow just wants to know, how do I relate this to the human body? And no, I don't think that the um, electricity starts at the heart. I think electricity is everywhere, and you can almost prove this to yourself if you want. If you want to do a little experiment, and remember, experiments are for proof. They belong to religion. It just gets you to believe something. It has nothing to do with theory. Okay, but pinch your toe, and you'll feel it instantly. Where are you feeling it? Well, you're feeling it in your brain, really. And you say, well, I feel it in my toe. Yeah, you feel it down there, right? But see, if you were quadriplegic, right, and I pinch your toe, you probably wouldn't feel it. More than likely, you won't feel it. And you say, well, why can't you feel it? I'm pinching your toe. I mean, hurting, it's bleeding, and you still can't feel it. And yeah, because you have some disconnection somewhere in your body that prevents the signal from going to your brain. Okay, so yeah, all that's tied in a single connection. Okay, everything's tied in there. And I'm saying that, you have these nerves, which are cells, and you have between them the synapses. And the synapses, which is this empty region that they never were able to figure out because it's an invisible no man's land in there. I'm saying that there you have material. You have either the ropes connecting that or some atoms or whatever. But there's something there, and that carries the signal physically all the way to your brain. If you were to sever, that region, like in the case of a quadriplegic that's got some disconnection there, then yeah, you won't have the signal travel all the way to your brain, and you can pinch his toe and he won't feel anything. Okay, so all I'm saying is I don't think it starts in the heart. I think electricity and magnetism are all over our body, as well as obviously chemical reactions of different kinds, right? So, I can't tell you where it starts. I don't think it starts anywhere. I think it's simply across the board. All your nerves are chemical, electrical signals, and I think magnetism is involved in that process as well. And other than that, I don't think I can give you more information. That's really for doctors and people who do research on the body. I don't specialize in bodies, except female bodies. Those I do specialize in. Okay, but anyways, here we have same fellow says, if the mechanism of temperature is the length of links in a rope, how does that apply to stratification of distillates? Does the complexity of the molecules and thus the number of ropes acting upon them determine specific gravity? Okay, so let's get the terms first in here. What's distillation? Here you have an example, okay, fractional distillation, okay, and you have different temperatures. for oil, and you get different products out of each one of those. Okay, and each one has a different specific gravity. Okay, so that's in a nutshell. Okay, what distillation is. Okay, let's take this out, and here you have a definition of specific gravity. What did I do with it? Give me a second here. On the other side. Sometimes it does that. The term specific gravity is used to define the weight or density of a liquid as compared to the density of an equal volume of water at a specified temperature. So different temperatures will vary also the density, okay? And that should be straightforward for people to understand. The temperature used for measurement is usually 39 Fahrenheit, 4 degrees, okay? Because this temperature allows water to assume its maximum density. Okay, so they look at water's maximum density and they peg all the values of all the other gases and liquids, etc., to that value. Okay, in the metric system, water has a density of 1 gram per milliliter, so density and specific gravity are numerically equal. Okay, which is a good benchmark. Okay. If the liquid you are comparing has a specific gravity lower than 1 gram per milliliter, it will float on water. Otherwise, it will sink. Okay, and there you see an example. Okay, they take that acid, mix it with water, and now it's got a different specific gravity. Okay, so this is the question that he's asking, saying, how does that relate to ropes? Okay, so let me show you first an example. Maybe we can get that notion across with an example better than anything else. Here we have the density of hydrogen peroxide. Okay, I use that quite a bit in the semiconductor industry. We had a lot of hydrogen peroxide around, and you can see how that density changes with temperature. Okay, so at close to low temperature, you can see that it approaches the density of water. But as the temperature rises, then that the density then changes. Okay, and the question is, why is that so? Because density is the specific gravity essentially. Okay, that's a measure of specific gravity. And here's an illustration of this that will maybe put it in the right perspective. Okay, here you have water. The water molecule. This is just a drawing of how the water molecule appears to be. You have this oxygen, big oxygen, right, atom, element, and you have two tiny hydrogens, okay? And what if we were to now turn that into hydrogen peroxide? Well, we would have to add another oxygen to that molecule, okay? So we would have two oxygens and two hydrogens, whereas water has only one oxygen, two hydrogens. But remember, oxygen is element number 8. Okay, that means it's got 8 electrons. It's got 8 balloons under the rope model. This is what it looks like, more or less. Okay, that's more or less what oxygen looks like. Okay, you have the p orbitals and the two s orbitals. The circular ones are the s1 and s2, and the others are the p orbitals. Okay, so this would be, if you had God's eyes, this is what the oxygen atom, the element known as oxygen, looks like. Okay, and yeah, it's not a little bead that goes around, which is the quantum mechanics version of the atom. They say the electron is a little bead that goes around those balloons. That's in that region. You can find it there. They're concerned about finding it, not about what it looks like. And it turns out there is no little bead called the electron going around. What you have really is balloons. But imagine each one of those balloons has at least one rope to every atom in the universe. You have to look at each one of those balloons as a hydrogen atom. So the oxygen molecule is made up of 8 electrons, or 8 hydrogen atoms, you could say, right? It's got 8 protons and 8 electrons. And it's this thing that you see there that is going to be added to the H2O, to the water molecule, to build hydrogen peroxide, double H, double O. Okay, so you can see that it's going to tend to increase the specific gravity of the water molecule. Okay, so the water molecule would be this, and the other one with the extra oxygen. You're adding 8 more hydrogen atoms, so to speak, to your molecule, to your water molecule, and so you're creating a heavier molecule essentially. Okay, at different temperatures, of course, it's going to have a different density if you have many of these molecules in there. But the point here is that each one of those balloons carries one rope to every atom in the universe, to every hydrogen atom in the universe. That means that if you have a carbon atom, right, element number 14, right, then how many ropes will you have? Well, you have a little more than oxygen. Okay, that's what you're going to have. And it depends on how many hydrogen atoms you are putting into an atom, right, to an element, a chemical element. Each one of those is going to have a rope to every atom in the universe, including to other balloons within that atom. Okay, so yeah, it's going to affect your specific gravity in that sense. Okay, so I hope you get a sense of it through the illustrations of what I'm trying to say here. I'm saying that for every hydrogen atom in the universe, you're going to have one rope. So the more elements, the heavier the element, the more hydrogen atoms you could say are made into that element. For example, in the case of uranium, you have 92 hydrogen atoms in one atom, in one element. Okay, they're merged in different ways, and I've talked about that in the past. Essentially, the membranes blend into each other, and they form these weird shapes there. It's like tying balloons, and you make all these many balloons around it, and imagine uranium 92 protons, 92 electrons, 92 balloons. That's 92 hydrogen atoms essentially. Okay, not to mention the neutrons, which surpass it. You have 235, 238 neutrons in that atom. Okay, but the point is that for every balloon you have one rope. Okay, and that of course makes the atom that element not only heavier, but if it's mixed with some other liquid or whatever, it's going to increase the density of that liquid, meaning the specific gravity. Okay. Okay, fellow says, time dilation is happening, isn't belief, hypothesis, or theory. It's a fact. Aha, time dilation is a fact. For GPS to function correctly, time dilation must be adjusted for. Okay, and so, okay, what is this time? Well, time, it's a system of sequential relations, duration. You look at duration, the length of time. Synonym, they go back to time. What is dilate? To make wider or larger, cause to expand, to spread out. So what this fellow is saying, that time dilation is happening, and otherwise clocks wouldn't work or whatever, GPS wouldn't work. And yeah, I guess time is expanding. How do you expand time? It's a concept. It's an undefined concept, but he's going to expand it. If it's a concept, I mean, you're not talking about a physical object. You can say a balloon expands, yeah. You can say the bubble gum, you blow it and make this big bubble, right? But to say that time expands, how do you do that? Does intelligence expand? Does love expand? Well, maybe he would say, yeah. Okay, yeah, you need to define time before you can say it's anything about like time dilation or whatever. Dilation, by the way, is a word that belongs exclusively to physics, has nothing to do with math, so can't even be borrowed. Okay, again, dilation means you make it wider, you make it bigger, and you can't make numbers bigger, meaning fatter, taller, more volume. Okay, it's not applicable to numbers or anything in math. Okay, same fellow says technology is into massive exponential growth. Well, I'm saying technology was over, especially when they invented the computer. That was the last time we had technology. Since then, we have some gadgets that are being invented, you could say, but they're not critical. I mean, the critical inventions happened at the end of the 19th century, beginning of the 20th. And that was, the telephone, the car, the airplane. Those were the inventions. Okay. After that, we had a few more, all the way up to, you could say, the computer, the chip, and then later the computer. And after that, all we did was put them all together. What is a cell phone? Well, a cell phone is not an invention. It's it's putting together several inventions. You put a typewriter, you put a radio, you put a TV, you put a computer, you put a telephone, you put them all together and you have a cell phone. So a cell phone is just a repackaging of all those inventions in one apparatus, in one device. That's all it is. So we haven't had any inventions, real inventions, groundbreaking inventions, and we won't have any. I mean, some people are expecting this singularity. You have Kurzweil, one of the fellows out there who vouches for the technological singularity, the point at which the computers and the robots out there will invent more things than human can possibly invent on their own, and they will take off and invent gazillions of technology that we cannot even imagine. What can I say? If you cannot imagine it, it will never happen, because we are supposed to imagine technology. Like you had Jules Verne, at the end of the 19th century. He was suggesting that we could fly with a balloon around the Earth or go to the moon. Well, people say, well, you're crazy. We can't go to the moon. It's impossible. And flat earthers still say that. But some people said, okay, let's see if we can get to the moon. And in the 60s, the end of the 60s, 68, right? Man went to the moon. Armstrong stepped on the moon, right? Some people say he didn't. Okay, that's fine. But we went to the moon. We had rockets, at least, that can go out there. And it was an invention that Jules Verne already had in the 19th century. For him, it was, science fiction. It was just wishful thinking. But then it became a reality. And that's just one example. You don't have to take it to the moon. You can get with the airplane. You can talk about the telephone. At some point, people said, hey, it'd be nice if I could talk to this person in New York. I'm in LA, And eventually this came to be. First they had the telegraph, then that went into the telephone and so on. And so, what was the idea existed already. It was there. It was in people's minds. And eventually it came true. But you have to have the idea before you can invent it, before you work on it. And today we have no new ideas for anything groundbreaking. I mean, what are we going to invent? The how to travel through the fourth dimension, with some device? Is that what is ahead of us? What invention can you imagine that we need? See, we need stoves to cook our food. Some people don't even need that. They just go to McDonald's and they have their stove over there. You need a fridge to, make your beer can go cold, and you need bed to sleep on. You need pillows to put your head on and so on, chairs to sit on, tables to eat on and so on. Those are inventions that we need. You could say we need them. We can't really do without them, or we use them every day. What invention can you even imagine? Forget about developing it. Just imagine your wildest imagination, right? Give me an invention that we need, that if you invent it, it will put millions of people, billions hopefully, to work in the manufacturing industry. Why do you think we have no manufacturing today? Because there have been no new inventions. And because whatever inventions we had, and we modify here, we make it blue instead of red, right? We put it on the assembly line. We have some robots and some people working on that, and all the rest of the people they don't need. They say, go home. And all those people work in services. So yeah, inventions had to do with the age of manufacturing, which is now over. It died, okay? Bury it, okay? Requiescat in pace, right? And so we will not be inventing any more gadgets that will at least put people to work, which is where we would need them, right? Creating jobs. And also gadgets that we need. I mean, what is it that we really need that we don't have that we absolutely need? And I'm not talking about games. Okay, that's not an invention. We'll see you next week. Bye bye.